Hello, hello, everybody. Am I coming in loud and clear? Can you smash that chat button if you can hear me? Hello, everyone. Wow, it's like an avalanche of yeses. Let's do this. Just looking at the responses for how people are today. 15 people are awesome. 36 people, okay. 11, meh, I don't care. And 4, bad, so very bad. I am sorry about that. I will try to make this hour good for you. So welcome back. Welcome to week 3. Just to remind you, I'm Chris Tisdale, and I'm a tutor for this course. And I've lectured this course many times in the past. So this week is a calculus week. I actually gave a tutorial on Monday where I actually did algebra questions, so I got a bit confused there, but I know what week it is today, so let's have a look at calculus. All right, so let me share my screen and we can have a look at some of the questions. All right, so you should be able to see this. So this is chapter 2. Let me just go up to show you the page number. So this is chapter 2, page 49 from the course pack. Okay, and you can get the course pack in Moodle. All right, so as far as I understand, you've been looking at limits in lectures for calculus. Now, limits are super important because they help us understand how a function behaves, okay? And we can use limits to work out, the behavior and continuity and all sorts of nice theorems. So what we'll do first is have a look at this question here, number 12. So in this tutorial, it's like a tutor-led tutorial. So I discuss some of the questions and we can go through them together. But mostly I'm going to be sort of talking and discussing stuff. But I definitely want everyone to just go crazy in the chat. Don't hold back. Okay. All right. So these ones up here, I actually did some of these last week. So like I did this one last week and a few other ones. So you can always see those recordings. But let's have a look at number 12. So we've got some functions and we want to find the limits, and the idea is to find the left and the right hand limits, decide whether or not each of the following limits exist. And if they exist, find the value of the limits. All right, Zach, today we're going to concentrate on calculus, but if we have time later, I'm happy to talk about algebra questions. That's fine. Yeah. So let's have a look. Let's have a look at question 12. Now, as most of you would know, I do like drawing stuff with GeoGebra. So I'm going to look at this one first, part B, and we can just do a curve of that in GeoGebra. So let me pull up GeoGebra here and we can share it. All right, GeoGebra Classic. So this is a picture of this function here. Okay, all right. So we want to find out the limit of this function as x approaches 2. So one of the nice ways here is just to draw a picture using GeoGebra or whatever, your hands, Desmos, whatever you've got, okay? But just looking at the picture, does the limit as x approaches 2 exist? I'm putting it in the chat, people. What do you think? Does the limit exist? Who can tell me? That's a big NO coming through. Well, that is correct. Can anyone in the chat say why it doesn't exist? Oh, Zach, you're one step ahead of me, buddy, because the right hand and the left hand limits are different. Shujun says two different values. They go to different points. Okay, so let's have a look at the picture. What is the limit as x approaches 2 from the negative side? What is the limit going to be? Who can tell me? -4, right? And what about positive? We approach 2 from the positive side. It's going to be +4. Yes, you guys rule. Okay, so enough GeoGebra. Let's actually write some mathematics down, and I'll just share my Chrome tab. Okay, so the question is 12b. So we know where we're going. Okay. And the function is, let me just pull that down. So I'm just going to write it out. So it's a split function. Oh, actually, it's not a split function. It's just a function like this. Okay, so don't worry about that. Now, of course, x can't equal 2 here. X is not defined. F is not defined at x equals 2 because we're dividing by 0, right? Okay, so I'll just make a note of that. Okay. All right. So let's compute the left-hand limit and the right-hand limit. So before we do that, though, let's simplify this a little bit. Okay, so I'm going to split this up into this thing here, right? So that's the absolute value of that. So when the thing inside is positive, this thing's positive, right? So I'll simplify that in a minute. And it's negative when everything inside is negative. Okay. So when is this true and when is this true? Well, let's just draw a little graph. That can be x squared minus 4. It's going to cut at 2 and -2. Okay. So if I wanted to work out what where this is, who can tell me? From this graph, where is this true? Can anyone say it in the chat? Come on, hit me up. Where is this actually true? It's definitely above the x-axis. And what x points does this, if you were to describe this in terms of x points, what x satisfy this? Yeah, Zach's on the case. Okay, so it'll be like here. So this is just x greater than or equal to 2, or x is less than or equal to -2, and this is the other bit. Okay, so I've just sort of squished that in there. Thanks, everyone. All right, so now let's simplify this thing here. We've got these different intervals, and we really want to approach x wants to approach 2. Okay, so let's work this out, and we can split it up. Okay, so for x here, the top bit, you can just get rid of the absolute value signs. Okay, so this is for x greater than or equal to 2, or x, oh, sorry, it should be greater than because x can't equal 2 in this case. Okay, that's fine, but we're excluding this. Okay, and for this, the top bit just becomes the negative of that. Okay, and that is for x between -2 and 2. Okay. All right. So now we can simplify. You can factorize this, and you're going to get the cancellation. So this is just x plus 2. And you can factorize this, and you can cancel, and you're going to get negative x plus 2. Okay? All right. So these are the two curves that we saw before in our GeoGebra picture. Okay? So we had the line x plus 2 and negative all of x plus 2. Okay, so let's actually work out the limits now. Okay? So maybe I'll just change my pen. All right, so let's work out the, I don't know, the right-hand limit. That's better. Okay, so in this situation, we're coming in from the right to the point 2. So x is bigger than 2 here. So is it the top definition or the bottom definition? Who can tell me what our f of x is? Is it the top definition or the bottom definition? Top or bottom? Smash that chat button. Yeah, it is the top. Good job, because x is greater than 2 here and x is greater than 2 here. Good job, everyone. All right. Now, what is this? Well, it's a polynomial. You can just put in 2 and you'll get 4. Oh my goodness, that's exactly what we saw before. So let's keep going. Let's do the other limit. 2 from the left-hand side. Now, who could tell me from the left-hand side, is it the top definition or the bottom definition? Let me know. I'm confused. Is it the top or the bottom? Yeah, it is the bottom, because here x is, sorry, that should be strictly less than, okay? Because here x is less than 2. Okay, it's polynomial, put in your value, you'll get 2 there, so the whole thing will be -4. So now we compare the left-hand limit with the right-hand limit, and they are not equal. Okay, they are not equal. So the limit as x approaches 2 cannot exist. Okay, so I'll take a new page for that. So we're about to make our conclusion now. Since the limit, the right-hand limit is not equal to the left-hand limit, we have that the limit of this does not exist. Okay. So if I was to go back to my GeoGebra, and let me just I'll put these back up in a second. So just give me 1 second here. Where are we? Okay. Yeah. So, I mean, you know, looking at the picture, you can say, of course, there's no limit there as x approaches 2. This thing's approaching 4 and this thing's approaching -4. So there's no way you can do it. And like when we wrote it down, there was just a lot of algebra and a lot of limit taking. You know, but it's super easy to just draw a picture and really work out what's going on. So our conclusion then is the limit does not exist. Okay. Okay, so the only really difficult thing with that question is simplifying to some really easy function. And you can see, I almost left that as a less than or equals to, but remember, x can't equal 2, so we can't have 2 anywhere in this definition. All right. Oh, Lucas, great question. What about the limit as x approaches -2? Let's go back to our GeoGebra and we can discuss that. That is a great question. So big thumbs up, I'll give that. And let me go there. Okay, so the question, week 3, what about x equals -2? So who can tell me in the chat, what is the function approaching as x approaches -2? 0, exactly. Okay, so the left-hand limit is approaching 0, the right-hand limit is approaching 0, and the function is defined at x equals 0, which is another thing. So yeah, Lucas, it's like a little corner, of, I don't know, a square or something, or a rectangle. Yes, it's sharp. So it's like a little corner of something. Okay. So yeah, like a kink. Now, a question for everyone while you're thinking about this and looking at the picture is f, let me just put this in the chat, continuous at x equals 2. Well, that should be a is. Is f continuous? X equals -2, sorry. X equals -2. Okay. Definitely continuous at x equals -2, right? I can draw a picture there and it's nice and connected and there's no jumps or anything. But at x equals +2, there's a problem, right? There's a jump. So the graph is not continuous at x equals +2. And CG, you're absolutely correct. The graph at x equals -2 is continuous, but not differentiable. Okay? Okay, Lucas, so Lucas, no, the graph is continuous at x equals -2. It definitely is continuous. And Juicy, you're right, there's a jump that occurs at x equals 2. So, okay, so you can see the method that Shujun, it's not differentiable because it's not smooth, right? So you've got this corner there that makes a difference. And what would a tangent line look like? Okay, Shujun, what would a tangent line look like here? You can't draw a tangent line, right? It's not going to work. Okay. All right. So yeah. So let's have a look at another question. What have we got here? I'll go back to I'll go back to 15. Okay. So let me share this one. This looks like a difficult question, but actually it's pretty easy when you know how. So this is 15. Discuss the limit of cos1 on x as x approaches 0. So we're looking at this one. Come here. Yeah. Okay. So it's got a h there, and the h stands for harder or more challenging. And people see this, they freak out. Don't freak out. Okay, you can do it. Sometimes students see these and they go, "Oh, that must be really hard." But actually, it's not that hard. It's just because they see the h. Okay. So discuss the limiting behavior of this function as x approaches 0. Okay, so let's do what we did before, and we can use GeoGebra to show the way. So I'm going to draw a picture, and this graph is not easy to draw, especially when x is small. So let's share GeoGebra, and yeah. So here's my GeoGebra, and I've got cos 1 on x there. Kapow! All right, so if I zoom in a bit, what's happening? Well, the graph is just a mess. It's oscillating up and down and up and down, and the graph is getting very tightly packed, right? So yeah, it's not quite clear what's going on, apart from it's a very complicated graph that is just oscillating and oscillating wildly. Okay, so does anybody have any suggestions for a strategy for this problem? Okay, does anyone have any strategies in the chat, or pinching theorem's an interesting idea. Let me share my Chrome tab. No idea. That's okay, Winnie, no problem. Let's write it out. Mohammed, I like your suggestion. Yeah, left and right is interesting. So the challenge is to compute, or to work out. I'm just going to turn this light down a bit. That's better. Compute the limit as x approaches 0 of cosine 1 on x. Okay. So let's take the suggestions from the chat, and let's consider the right-hand limit first. So I'm going to consider the right-hand limit. Okay. Now, what happens here, it's not quite clear. All we know that is as x approaches 0 from the right, this thing is going to get large and positive. Okay. And we don't really know what happens to cosine when that happens. Okay. So I'm gonna make a substitution. I'm gonna let u equal 1 on x. Okay. So we can let u go in there, and as x goes to 0 from the right-hand side, what does u go to? As x goes to 0 from the right, what does u go to? Yeah, a very big number, very big positive number. So positive infinity. Jia Hong, thank you. Okay, that's not 8, that's infinity. Yeah, infinity. Thank you, thank you. Okay, Ziwen and Fei Yui, thank you. Okay, so now let's replace this with a simpler limit. And I'm writing a lot here, but you don't have to write all this. So u is approaching positive infinity, and I've got cosine of u. Okay. Thank you, Shujun and Tash. Okay, so now what is this? Okay, good question, Fard. Let me show you. Let me draw a picture. Here's the x-axis, here's the u-axis. U equals 1 on x. As x approaches 0 from the right, u goes to positive infinity. Okay? Mm. So who can tell me what is this limit? Go crazy in that chat. Don't hold back. Does anyone know? What is this limit? As x goes to infinity, a few ones coming through. Let me go up to the, I'm seeing 0, 1, number between 1 and -1, undefined. This is great. I'm loving the chat. Let me show you a picture. And I can go back to my GeoGebra. So this is a very simple limit, but it's sort of deceptively simple, right? So you can see this is the cosine function here. And if we go to the right, it just repeats. It just goes up and down and up and down, and it doesn't approach any value, okay? So the limit of this is not defined, okay? It just goes up and down and up and down, as someone said in the chat, between 1 and -1. So you don't know what it is. It doesn't have a limit, right? It doesn't have a limit. You can't say, so it doesn't have a limit. So let's have a look at that, and we can then finish our problem. Okay, so this is undefined. So I'm going to, which does not exist. So if the right-hand limit doesn't exist, like that limit doesn't exist, that limit doesn't exist, so that limit can't exist. Okay? Hence, this limit does not exist. Oh well, at least we're happy because we solved the problem. I know. They're having a crisis about their existence. Do I exist? Oh, I don't exist. Okay. Yeah, ZG, exactly. If you can form something like cosine x over x or something like that, then yeah, that's no problem. But this is different. This is different. Okay? Yeah, if one of the limits doesn't exist, then this thing definitely cannot exist. Should you know, we don't need to do the left-hand side, because this limit, there's no way this limit can exist if this doesn't exist. If this doesn't make sense or doesn't exist, then this has no meaning. Okay? So we want to work smarter, not harder, and just looking at one limit is enough here. Yeah. Okay, let's go back to the program. So I'm just going to go into chapter 3 now. And chapter 3 is about continuity. Okay? So, Mario, I've only got, the question is, that's a good question, Stephen. You might recognize, I've only got Luigi this week. Mario's just chilling. He'll be back though. Maybe, who knows, maybe even the Yoshis will come. Stay tuned. All right. Let's go here. All right. So this is now chapter 3, page 60. Okay. So this is on Moodle. And chapter 3 seems to be about continuity and continuous functions and limits and stuff. So I'm going to do just a couple of questions here. I think I'll do question 2. Okay. Or actually, no. Let's do question 1 first. Let's start off a little easier. Okay. So suppose you've got a function that is basically the absolute value function. Show that f is continuous at 0. Is f continuous everywhere? Give brief reasons for your answer. So it's like a 2-part problem. Show that f is continuous at 0. Is f continuous? When they say everywhere, they mean at all points in its domain, okay, in its biggest domain, right? Give brief reasons for your answer. Okay, so first of all, let's understand what the absolute value function looks like. Okay, and I'll go back to GeoGebra, and I will share. Hang on, let me just pop that up. Yep. All right, so let's get rid of cosine x, and here is, let me just put that in. Here is the absolute value function. Okay, so this is a graph of the function. Okay, so the question is this function continuous at x equals 0? Who can tell me on the chat? Yes or no? Is this function continuous at x equals 0? Lots of yeses coming in. Oh, thumbs up, Jeff. Good job. Oliver says no. Okay, Oliver, why not? Let us know what you're thinking. Have a think about it. It bounces off the line. Okay? But I guess the way I'm thinking about the continuity here is, can I draw the graph without taking my pen off the page? I can definitely do that. Okay? So I think on that definition, it really is continuous. Okay? It's got this corner here, but that's not a problem. So that's one way to think about continuity. So let's look at the other way, which sort of involves the limit, playing around with limits. Okay, so let me share my screen. Okay, there we go. All right, so this is question 1 in section chapter 3. All right, so consider f of x, which is defined to be the absolute value function. Sorry, my writing's not very good. Okay, absolute value function, which is x if x is bigger than or equal to 0, and negative x if x is less than 0. Okay, so you've got this situation like I had up before on the screen, where for x greater than or equal to 0, it's just the x function. For x less than or equal to 0, it's the negative x function. Okay. All right. So we kind of think, at least from the picture, that this is continuous at x equals 0 because I can draw that curve and not take my pen off the paper. Okay, so it's a nice continuous curve. But let's do it using limits, because I think that's the way they want you to do it. Okay, so consider, please, the left-hand limit and the right-hand limit. So the limit as x approaches 0 from the right, so that's here. So we're coming in that way. It's going to be the x function. Okay, so that's just going to be 0, and coming in from the left, it's this function here, negative x. That's also 0. And lastly, what is the value of the function at x equals 0. Well, when x equals 0, it's that, which will just be 0. So we compare these three things. They're all equal. And we can conclude that this limit exists. And it's equal to the value of the function at 0. And so our f is continuous at x equals 0. Okay, so this is the key thing. This is really what you're testing here. This has got to be well defined and equal to this, and both of these limits have to be equal. So they have to be all equal to the same thing. Okay, if one of those things is not matching, then it's not continuous. Okay, Sam, couldn't you also have x less than or equal to 0 with the next? Yeah, you could. You absolutely could, Sam. You could break the definition and go, well, you know, I'll just have x positive and x less than or equal to 0. You could definitely have that, Sam. Not a problem. I'm liking the way you're thinking. Accept nothing. Challenge everything. I'm loving it. Okay. Taj, great question. If you get an equation, how do you know what x value or values to test? Okay, so brilliant question. So let me go back to the question as it sits in the course pack. So show f is continuous at 0. That's your x value right there. So we were approaching x equals 0. That kind of told us where to look. Okay, so that's the first part of the problem solved. Is f continuous everywhere? Part B, let's have a look at that. Is f continuous everywhere? So that sort of means, is it continuous at all points in its domain? So let me go back here and pop GeoGebra back up. So have a look at the graph. Is there any points where the function's not defined or the graph is not defined or where it jumps? Yep, you're absolutely correct. So there are no points where it's not defined and there's no points where it jumps. So it's got to be nice and continuous. Okay, so let's make a note of that on our sheet of paper. Okay, so this is part A, and this will be part B. So also, f is continuous everywhere. So that means at all points in its domain. And they're asking us to provide a brief justification. So how might we do that? Yeah, Amelia, great comment. So Amelia said, because we know that y equals x and y equals negative x are continuous, and it's continuous at x equals 0. I'm going to steal that, okay? Because, I'm even quoting you, because we know that x and negative x are continuous. They're polynomials, right? Let me grab a different pen. They're continuous, so they're known as polynomials. Polynomials. So they're continuous everywhere. And our function is continuous at x equals a. Okay, yeah, all polynomials are continuous. Yeah, polynomials, CG, absolutely. They're the really friendly functions, right? Quadratics, linear functions, cubics, quartics, they're all very fun and friendly functions. Okay, they're all fun and friendly functions. So part B is a little bit like what you might get in your writing assignment. In the writing assignment, you get some questions and you're supposed to use proper English and proper grammar. Obviously, don't use words like that. That's supposed to be because. But it is important to be able to write sentences correctly when you're describing or explaining mathematical solutions. Okay. I think we have time for at least one more question. So let me go back to, go back to the questions. All right, part 2. Determine at which points each function f is continuous and give reasons. So let's just look at this function. Okay, it's a split function. It's been defined in a couple of ways, depending on what x is. Let's have a look at the picture and we can see a little bit more about what our function's doing. Okay, so let me bring up, you guessed it, GeoGebra. Okay, here's one I created earlier. Pam. All right. So the question is this a continuous function? You've got the cosine function on the right of 0 and exponential e to the 2x on the left-hand side. And we've put them together. Is it continuous? All right, everyone's saying yes. Jason and Zach, Han Young, Chloe, Oliver, Juza. Absolutely. You're right, it is continuous everywhere, including where it changes. Like you can see here, it changes from one function to another function. But if we zoom all the way in here, it looks from the graph that it's a connected curve here, right? Okay. So Shinyi, is every time we do this type of questions, we need to draw a graph first? No, you don't have to. It just helps me understand the problem and it helps me explain it. So when I'm giving these classes, I write a lot and I use technology a lot to show what's going on, but I'm explaining it to everyone. Okay, you don't need to do exactly what I do. Yeah, you got it. So let's have a look and see what's happening now. So it looks like it's continuous, and let's work out the way you would do it with limits. So let me share. So this is 2. Okay. So consider the following function. E to the 2x for x less than 0 and cosine x for x greater than or equal to 0. Okay, so now this is obviously a continuous function because it's an exponential function. This is a nice friendly continuous function. And The only question is what happens at x equals 0. Okay, so let's just give a few reasons. It's continuous everywhere. Cosine x is continuous. I'm just abbreviating this. Okay. And the last thing we want to do is show the continuity at x equals 0. Okay, so let's do that. So finally, we want to show this limit. Okay, so the first question is, what is f of 0? What is the value of f of 0? Who can tell me in that chat button? It's 1, okay, good, loving it. So we go in here, we go, okay, well, here's the definition for x equals 0. So that's the easiest part. Thank you, everyone. So let's think about this limit now. So the limit as we approach 0 from the left, that's when x is negative, it's going to be this. Okay, so we know we can just put 0 in there and get e to the 0, which is 1. So that's looking good. And limit as x approaches 0 from the right, well, that's when x is greater than 0. So it's this thing here. That's the definition we want to use. And this is a nice, friendly, well-behaved function. You can just shove that in and there. So our two limits are equal. And they're equal to the value of the function. So happy days. So let's make a conclusion. Hence, star holds. And f is continuous at 0 and everywhere else. At 0 and everywhere else. Okay. All right, Mohammed, that is a great question. What type of functions aren't continuous? Ooh, that is a good question. That is a really good question. Okay, so let me draw a function that isn't continuous. Okay, so let's have a look. Let's have a look. So I can draw a function pretty easily that's not continuous. Okay, so here, I'll put that up a bit. Here are my axes. Okay, I'm going to draw a function that looks like this. Okay, let's say that's 4. So you can see, Mohammed, that this, just from the graph, if I want to draw the graph, I have to go up there and then take my pen off the page and move it down here. That's not continuous, okay? So this function is not continuous. So it's a case where you have jumps or it's not defined, okay? All right, so I hope that helps you. So Ling Tang, for the last question, how about if a question asked to show that f is continuous at x equals 1? Oh, good question. Okay, so at x equals 1, this is obviously bigger than 0. So I would just say cosine. It's well known that cosine is a continuous function. Okay, I think it would be very unlikely that you would get asked that though. Okay, so I would just say, look, cosine's a continuous function, and it's definitely continuous. If you wanted to show that, you could. It's up to you though. All right. Fair Yui. The reason we want to prove if f is continuous at 0 is that x equals 0 is the point that connects two different functions. Yes. Yes, that is correct. Let me give that the big thumbs up. Yeah, that's perfect. Okay, we're just checking what happens with when the functions change the definition. So that is a very good question. Okay, Zach, how can we practice our skills? Good question. There will be practice exams coming out for before like lab test 2 and lab test 1 and the final. So there'll be some practice exams. That's the really important thing. So practice, get to know Maple well. They're the best. That's the best advice I can give you. All right. Mohammed, are there names from them? Yeah, there are categories of discontinuous functions, like removable discontinuity. We'll talk about those later, but you can classify them. Okay. Oh, Ling, you're talking about the first question. First question. This one. Is that correct? Okay. So the question is, what happens if you are, I think if you are asked to, is this function continuous at 1, I would just say it's a polynomial, and all polynomials are continuous. Okay, that would be my response to that. Okay. Yeah. Hey, Chloe, you want to come in and say hi? Hey, my daughter's here. You want to give him a big say hello? This is Chloe, my daughter. Hey, how you doing? She's just got home from school. Okay. They're all saying hello. Okay, they're wondering where Mario is today. All right, everyone, I think it's time to go. So I'll see you same time, same place next week. Enjoy, have an enjoyable week 3, and yeah, we'll see you next week. Bye, everyone. I'm going to go.